Okay, let me actually repeat that one. So the one I just did not record it. So so last time we talked about the two different numeric system. One is the decimal system, the other one is binary system. Even though decimal system and binary system looks very different, you know, in the decimal system you use the 10 symbols, and the binary system use only 2 symbols, 2 digitals, 0 and 1. Okay, now even though they look very different, but mathematically they are equivalent, or which means that you can always find a mapping between 2 different type of numbers. So for every decimal number, you can always find a binary representation, and for every binary number, you can always convert it into a decimal number. So there's a 1-to-1 mapping between these 2 numeric system. Now, so for the decimal number, you can always represent any numbers in terms of the sum of the power of 10. So here I gave you an example like a 596. So 596. So you can write as, you know, for number 6. This is on the, you know, the rightmost position, and that's called a ones position. So for the number in a ones position, number 6, it's always multiplied by 1, which if I write as a 10 power of 10, 1 can be write as 10 to the 0. Okay, so it's a 6 times 10 to the 0, or 1. Now the number in the second position, that's called the 10th position. So every number in this position, it's actually 10 times bigger than the same number in one's position. So that means if you have a 99, that 9 represent 9. This 9 represent 9 tenths times 10. So it's always 10 times the bigger than the one's position. So in here, the 9 actually can be represented as 9 times 10, or I can express as 10 to the 1. So which is the same as the number 10. Now, the next position is called the hundredth position. So every number over here, it's actually 100 times the number of the same number in the ones position, or 10 times the same number in 10th position. So it's always, you know, 10 times bigger than the previous, the same number in the previous position. So in here, 5 is in 100th position, which means every number 5 should be multiplied by 100, or equivalently I can write 10 to the 2, which is 10 squared. So that's basically how I can represent a decimal number. Now, for the binary number, remember I only allowed to use 2 digitals. So every binary number going to be write as 1 1 0 1 0 1. There's only 1 and a 0 appears in that number. If this is a binary number, to tell that this is not the decimal number, I normally put the 2 in the subscript, you know, subscript 2. So for binary number, so every number on the rightmost is called a ones position, just like the decimal number. And the next position is called twos position, because if I cannot represent a 2 in single digit only, so if I actually reach number 2, then I have to use the next position to represent it, and that's called twos position. Okay, and next number is called fourth position, and the 8th position, and the 16th position, and 32th position. Now you just remember that every time when I actually write the number, this is ones, and the next one is twos, next one is fourth. So every position on the left is always double the previous one. Okay. So For this number, I can always write as 1 for this number. It's in the ones position, so it should be 1 times 1. Okay. Since actually it's a binary number, so I can always write as the base of 2. So I can write as 2 to the 0. This is a 1. 2 to the 0 is 1. So it's ones position. The number 1 should be multiplied by 1. Okay. And then the next position is 2's position. So it should be every number over here should be multiplied by 2. Now the number here is 0, so it should be 0 times 2, which is the same as 2 to the 1. Okay, so 2 to the 1 is the same as 2. And then the next position is 4th position. The number is 1. The value is 1. So it's 1 times 4. And then the 4 can be written as 2 squared. Okay. And then the next one is 8th position, or which is 2 cubed. And the value is 0. Okay. The value is 0. And the next one is 1. Okay. But the position is 16th position, which is 2 to the 4th. Okay, I'm running out of space here, but so then the last one, that's this, 4th position. And the last one, the leftmost one, is 32th position, which is 2 to the 5th. The value is 1, so 1 times 2 to the 5th. Okay, so the number 110101 should be right as 1 times 2 to the 5th, plus 1 times 2 to the 4th, which is 16, plus 0 times 2 to the 3, 1 times 2 to the square, and 0 times 2 to the 1, and then 1 times 2 to the 0. Okay, so that's a difference. So every binary number can be written as the sum of the power of 2. And here, every decimal number, it can be written as the sum of the power of 10. So that's the reason why we call the decimal number a base 10 number. And this binary number is called a base 2 number. Okay. Now we just mentioned that how can we, convert between a binary number and the base decimal number. Okay. Now, one direction is very simple. If I have a binary number, if I want to actually represent in terms of decimal number, then you just use that expression and calculate it out. Okay. Now, what is the value for this, the decimal value for this binary number?
53.
Wow, that's good. 53, right? Okay. Why is that? Because you can actually write as 1 times 2 to the 5th, that's 32, and then plus 1 times 2 to the 4th, that's 16. So it's 32 plus 16. And the next one is 0 times 2 to the 3, so that's 0. And that's 1, that's 4. So that's 4. And 0, so you don't count this one, and that's 1. So that's 1. So you basically add these numbers, 32 plus 16 plus 4 plus 1. So what is that number? Let's see. Yeah, that's 20. Yes, that's 53. You see that number? You see the, so that's something we just talked about last time. And now this is the easy part. If you have a binary representation, then you can easily convert into a decimal number. But on the other hand, if you have a decimal number, to convert it into a binary number, you have to do the division by 2, right? You keep doing the division by 2, and record the remainder and write the remainder in the reverse order. So that's basically what it is. So I'm not going to actually talk much about this. This is actually one of the example we used last time. Okay. Okay. So now, so for every number we actually use in our life, it's a decimal number mostly. So most people don't use binary number. However, some people teaching math, they use the binary, but most people they use decimal because decimal is actually easy to use, and we get used to it. Now, the reason we want to learn the binary is because we want to know how the computer system, store and operate the numeric system. Because computer system, remember, it's a device that deal with the binary digitals, the binary numbers. So every number, regardless it's what the type or every data, it will eventually convert into a binary digitals, and the store as a binary digitals, and the operator on the binary numbers. So that's the reason why we need to learn binary numbers. Now, the most widely used operation is addition. Okay. So when we add two numbers, okay, so we just need to use the addition table. Okay. So the addition table we just mentioned here. For binary, the addition table is 0 plus 0 is 1, 0, 1 plus 0 is 1, 0, 0 plus 1 is 1, and 1 plus 1 is 1, 0. So that's something we need to know. Now, in the decimal operation, we know that we use the addition table for the decimal number, but the addition table for the decimal number is pretty big, right? So if that's addition, and then we need to actually list the 0, 1, 2, 3, 4, all the way to 9. 0, 1, 2, 3, 4, to 9. So then you can say, okay, what's the value of 3 plus 4? 3 plus 4 is 7. So we just basically 0 plus 0, it's 0. 1 plus 1, that's 2. 0 plus 1, that's 1. So you basically fill out the number. That's called addition table for the decimal numbers. Now, that's basically the table for a single digital addition. Because when we actually ask the computer system to perform the addition, then we need to actually tell the computer system what is the result for the single digital addition. So same thing for the multiplication. We need to actually know what's the single digital multiplication. But at this moment, we just only deal with the addition. Now, with the addition table, then we can easily do the addition of multiple digitals. For example, if I add two numbers, 596 plus 27. Okay, so then how can we do this addition? So we're going to actually first add the number in ones position. So 6 plus 7. Now, what's the value for 6 plus 7? We know it's 13 because when we look at the addition table, 5, 6, 6 plus 7 is going to give you 13. So that the addition table is going to show it's a 13. So then this is 13. Okay. 6 plus 7 is 13. Okay. So, however, it's a 3 in the single digital, but there's another 1 in tens position. However, so we're not going to actually, the result in tens position is not 1 because you have two more numbers. So basically, we'll put that number over here. Okay. So then I'm going to erase. I am going to erase that number over here. So, and then we're going to add the numbers in tens position. So 9 plus 2, that's 11, plus the 1 just carried over from 1's position. So 9 plus 2, 11, plus 1, 12. So it's a 12. And I put the 1 over here. Okay. Instead of actually put the 1 down over here, we'll put it over here because we need to add that one with the numbers in 100th position. So this one just carry over from 10th position to 100th position. So then 1 plus 5, that's 6. There's no numbers carried to the next position because 1 plus 5, it's still a single digital. If any number add together, it's a double digitals, then one digital should be carried over to the next position. So this is actually what we got. Now for binary numbers, we actually do the similar things. Okay, so 0 plus 1, that's still 1. That's a single. It's still single digitals. Now 1 plus 1, so it's a 1 0, 1 0, and a 1 should be in the next position. So instead, I'm going to put the 1 over here, just carry over from here, right? So it's 1 0, and then I'm going to add a 1 0 0, which is actually in the 4th position, and that's 1. And then they add these two numbers, and you got a 0 and a 1. Now you have 1 carry over from the previous position plus the 1 or 2 ones over here. So you got a 1 plus 1, it's 1 0, plus 1 is 1 1, so it's 1 1. Okay. Now 1 plus 1, that's 0, carry over to the next position, and then that next position should be go here. So this is the final result. Okay. Now, if you have any questions on the binary addition, just let me know, because it's very important. Now, also in the decimal, you're going to also deal with subtraction. So two actual numbers, one minus the other number. Okay, so we can do this. Now, you also need to remember, so just do the single digital subtraction. Okay, now if the single digit number above the top number is smaller than the bottom number, then you need to borrow a number from the next position, right? In 1's position, so you need to borrow a number. But so that's the subtraction for the decimal number. However, now in the binary system, we can avoid this subtraction. We can avoid the subtraction by introducing a new binary notation. It's called a tooth complement notation. Okay, so once you introduce the tooth complement notation, then you can basically represent both the positive numbers and the negative number using the tooth complement, representation. Okay, so the tooth complement system, in the tooth complement system, we use fixed number of bits. Remember, it's a fixed number of bits to represent both the positive and negative values in the system without introducing a plus or negative sign. Because remember, if you don't use the tooth complement, now for every actually binary numbers, now we have to introduce additional bit for the sign, right? For example, I can use 0 to represent plus, 1 to represent a minus. Okay, so then here you can use a binary representation. Okay, but in the tooth complement system, we don't have to do this. Okay, so here's what we can do. So here's the general rule for the tooth complement representation in the computer system. Now remember, the computer system use a fixed size, to store a number, an integer number, whether it's positive or negative. Okay. Now, so for example, in Java or most of the computer language, we use for integer type. If you declare an integer type, int x, then x is an integer type. So that basically means, the computer going to reserve a memory space, which is 32 bits. To store that number. Okay. 32 bits. Okay. Now, with the 32 bits, then you can represent both a positive number and negative number. Okay. Now, to actually illustrate this case, we're not going to use 32. So normally we use 4 bits or 8 bits in our example. And later we will find out 32 bits is very similar to 4 bits and 8 bits, but because 4 bits and 8 bits are very short. Okay. So with tooth complement notation, you know that a positive value written in tooth complement notation is the same as the value written in unsigned notation, although we must explicitly fill a 0 in the most significant bit. Okay. Then a negative value can be written in the tooth complement notation by inverting all the bits of its absolute value and then add a 1 to the result. Now, these are general rules which tells you how to represent a positive number or a negative number into a tooth complement notation of certain size or a fixed number of bits. Now let's take a look at the example. Okay, so suppose we try to, write a number -6 in tooth complement notation in 4-bit system. Suppose the system we're using is 4 bits. Okay. Now, we want to write a -6. Now, before we do this, first we need to know how to write 6. Okay, how to write a 6 in tooth complement notation. Now, suppose I have a 6. Okay, the tooth complement system, I use 4-bit system. Okay, I use 4-bit system. Now, how can I represent number 6? What is the sign for number 6? Is it positive or negative?
Positive.
Positive.
Okay, 6 is positive, right? Because I don't have a negative sign before it. Now for positive, now what's the rule?
0.
A positive value written in tooth complement notation is the same as the value written in unsigned notation. So that means, so I'm gonna simply convert number 6 into a binary number, right? Now, what is the binary number for 6?
0110.
110. So that's 1's position, that's 2's position, that's 4th position, that's 2's position. So it's actually 4 plus 2, that's 6. Now, if I have to write into a tooth complement notation with 4 bits, then I have to add additional 0 to make it 4 digital. Okay, so that's the 2's complement notation. That's a 2's complement notation for number 6. Okay, with 4-bit. Okay. Now, what is -6? So, for -6, the general rule is, first, a negative value can be written in the 2's complement notation by inverting all the bits of its absolute value. Okay, so the first one is for -6, I'm going to convert it into I'm going to actually first put the absolute value. So that means I'm going to get rid of the negative sign, which is 6. Okay, and then I write 6 in terms of binary system, right? So that's 1, 1, 0. That's this, right? Same. And then I invert it. Invert each of the bit. So 0 becomes 1, 1 becomes 0, 1 becomes 0, 1. Okay. Now after inverting each of the bits, then I add 1 to it. Add a 1 to it. So 1 plus 1, that's 0, 1, 0, 1. So the 2's complement notation for -6 is this. Okay. So the 2's complement notation for 6 is 0, 1, 1, 0, and 2's complement notation for -6 is 1, 0, 1, 0. Okay. Just follow the rule. Okay.
Excuse me, Professor, can you please re-explain the last part of it after inverting the numbers?
Okay. After inverting the numbers, right?
Yeah.
Then, based on the rule, add 1 to the result. Okay. So you add a 1 to that result. Now, that's a binary addition. 1, 0, 0, 1 plus 1. So 1 plus 1, what is the result?
10.
It's 1, 0, right?
1, 0, yeah.
1, 0. So then 0 is here, and 1 going to be carried to the next position. And then the next position, it's a 0. But you have to actually add the 1 carried over from the previous position. So it was 1 plus 0, that's 1, right? Okay. So now this position, it's 0 already. So you just copied that. It's a 1, 0, 1, 0. So you just add these two numbers. Okay.
Okay, thank you.
Now we're gonna actually do more examples in this case. Okay. Let's okay, let's see this. Okay. So here, this is the process to convert a decimal value -6. So first, the -6 actually, you get the absolute value, which is 6. So the binary number for 6 is 0, 1, 1, 0. And then after inverting the bits, so it's 1, 0, 0, 1, inverting the bits, right? After inverting. Okay. So it's 1, 0, 0. Then add a 1. So then you add a plus 1 here. So this one, add a 1 is 1, 0, 1, 0. So that's 2's complement notation for -6. So -6, when stored in the computer system, is 1, 0, 1, 0. Now assume that computer system used the 2's complement of 4 bits. Okay. Now, so this is actually how I'm going to convert a decimal number, the number we're using, the numeric system we're using, into the computer actual binary system, the two's complement notation, which is going to be stored in the computer system. So it's always going to store as the two's complement. Now the other way, so once the number is stored in the computer system, if the number is 1110, now this is interesting because once you convert -6 into a two's complement notation, you will always find out that the most significant digital is always 1. So that means if the most significant digital is 1, that means this number is negative number. Okay, it's a negative number. Okay. So if that number is 0, that means it's positive number. Okay, that's always the case. Now, back to the other direction. If a number is stored in the number stored in the computer system, the computer memory is 1101 in two's complement notation with 4 bits. So then, before we convert into a decimal, first thing we need to decide is, what is the sign of this number? Is this a positive number or negative number? We first need to know that. Okay, because if it's positive, then the process is different from when the number is negative. So in this case, the number is negative, right? Because the most significant bit is 1. So the number is negative. So we need to first make a decision what is the sign of this number. So this is a negative number. Now, if it's a negative number, when we convert into a decimal, this is how we're going to do it. So the first thing you're going to do is invert the bits. Okay, so each one going to be a 0. 1 1 1 0 0 becomes 0 0 0, and the 0 becomes 1. Okay, so then we're going to add a 1 to that number. So 0 0 0 1, add 1. So 1 plus 1, it's a 0 1, and then 1 0 0 1 0. That's the addition of these two numbers. Okay, so then we convert this number, this binary number, to decimal number. So what is the decimal value for this number? It's a 0 0 1 0. So that's 2, right? Okay, now this 2 is the decimal absolute value. However, we know that this is a negative number, so that the actual decimal value is -2. Okay, so that's why this is actually -2. That's for the, encoding -6 into complement, two's complement notation for 4 digit. And the B, we basically decode the two's complement into 4 digit. Now that's just for 4 digital. But for if the number system use 8 digitals or 16 digitals or even longer, now what we do? So let's actually take a look at the example. Okay, now I'm going to use the same example, the same number, okay, to see how you're going to actually represent in the two's complement notation, because how many digitals of this two's complement system, that's very important. Okay, let's take a look. Okay, now here's something I want to do. Okay, now if I want to do, okay, I represent, suppose we use two's complement of 16 bits. Okay, so that means every number will be stored in 16 bits. Okay. Now, how the number 6 will be stored in the tooth complement system of 16 bits? So first we converted, because it's a positive number, so the 6 will be converted into a binary number, right?
Yeah.
It's a 110, right? Now, however, because we're going to store this number in a tooth complement system of 16 bits, so that number has to be converted into a 16 bits. So the actual number stored in the tooth complement tooth complement system going to be 0, 0, 0, 0. Let's say 4, 4, 4. That's 4, 4, 4, 4, 16. So that's the actual number stored in this. So you have to fill the 0. So if in the computer memory, you have to actually fill like a 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 1, 1, 0. Okay. Now, this is a positive number. So the most significant bit is 1. It's 0. So that means it's positive. Okay. Now let's see, what about the negative 6? How can I represent a negative 6 in there? Okay, for negative 6, first we look at the absolute value, which is 6, right? And then what is the 6 represent?
110.
110. And then you have to add a 0 here. So okay, 4, 4, 4, 4. Okay. And then in order to store in terms of tooth complement, what's the next step? Invert. Okay. So that means it's a 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, right? So every 0 becomes 1, every 1 becomes 0. So invert it, okay? Okay. And then what's the next step?
Add 1.
Add a 1. So you're going to add a 1. So it's a 1 plus 1, that's 0. 1 plus 1, 0. And also put the 1 here, carry 1 to the next position. And this 1 plus 0, that's 1, right? 0, 1, 1, 1, 1, 1, 1, 1. Okay, so that's tooth complement representation for negative 6. Okay. Now, how can I know it's negative? Because for negative number, the most significant bit is always 1. Okay, so that's why that means it's negative. This is actually means it's positive. Okay. Now when we actually try to convert this back to decimal, how to convert this one back to decimal. So you invert the bits, right? So how to convert back to decimal. Now, first we need to decide what is the sign of this number. So this is actually negative number because this is actually most significant is 1. So in order to convert, first, what's the first step? Invert bits. So this becomes 0, 0, 0, 0. 13 zeros. So so you got this 0 becomes 1, this 1 becomes 0, this 0 becomes 1. Okay, now all this 1 becomes 0. So you invert the number, right? Does it make sense? So this is the number you want to convert back to decimal. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You have 13 ones. So these 13 ones going to be converted to 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then the next 3 digits, 0, 1, 0 becomes 1, 0, 1. Okay, so after the inverting, what's the next step?
Add 1.
Add 1.
Add 1. Okay, so you plus 1 here. And this becomes 0, 1, 1, and then all 0. Okay. So then convert it into a binary, this binary number to a decimal, which is 6, right? Now, because we know at the very beginning that's a negative number, so the number is -6. So we convert it back. So it's kind of magical that, you know, when you convert to it, you actually, you know, convert the absolute value of this number for negative, the absolute value of into the binary number, and then invert the bits, add 1. That's a binary. That's 2's complement representation. Now, if it's a 2's complement representation, negative number of 2's complement representation, you first invert the bit, add 1, and then convert back to the decimal, and then add the negative sign. Okay. So that's the way. Now, for positive number, you don't have any problem, right? For positive number, if this is the number you want to convert into a decimal, because it's a positive, so you just directly convert this number into a decimal, which is 6. You know, there's no trick in there. So that's basically how you can actually convert back and forth between the decimal number and the 2's complement notation. Now, in this case, the 2's complement notation also include a positive number and negative number. So that's basically the trick we're going to play. Okay. So now, once we know how to do this, then we can actually play with, you know, all this addition and subtraction in a computer system. You know, of course, the computer system is going to do this based on this 2's complement addition. We're not going to actually do this. We just need to know how the computer actually does that. Okay. So here, this 2 table gives you the conversion between decimal number and the 2's complement representation. And the left table basically is in 3-bit system, and this one is in 4-bit system. So this gives you like a 7. It's a 0, 1, 1, 1. You know, it's a positive sign, so it's 7. Okay. So if the most significant number is 0, then it's the same as the binary representation, you know, of the number. Now, if it's negative sign, if it's 0, 1 here, Then 1111 is actually -1, and the 1000 is -8. Okay. Now it's pretty simple. Let's pick this one, okay, to see why this decimal value is -1, because you can see this 1111. So in order to figure out what is the decimal representation, because 1111 you have 1 on the significant bit, so this is a negative number, right? So for negative number, when you convert it into a decimal value, so you first invert the bits, right? 1111 becomes 000, invert the bits, and then add 1. So this is 0001. So, and then convert it into a binary, convert it into a decimal number, which is 1. And since it's negative value, so it's at -1. Okay. What about this? So first invert the bits. So it's 0111. Okay. Then add 1. So that's 0, 1, 1 plus 1, 0, 1 plus 1, 0, 1, so 1. Okay. So what is this value?
8.
8. Now, because it's a negative, so it's a -8. So this gives you some kind of idea. So this is gave you the conversion for 4 bits. Now you can build actually you can build 8-bit system, 2's complement notation with 8-bit, but that table is actually much longer because you can represent a bigger range, right? So for 3 bits, you can represent number from 3 to -4. For 4 bits, from 7 to -8. Okay. Now let's take a look at the how you're gonna actually perform the addition. So again, we are actually doing all these 2's complement notation of 4 bits. Okay, 4-bit system. So if we directly do the addition, 4 plus 2, that's 6, right? -3 plus -2, what is this?
-5.
-5. 7 plus -3. 7 plus -3. So it's the same as 7 minus 3. So that's 4, right? Okay. Now let's check how can we do this using the 2's complement. Because this is what we do, but we want to actually convert it into a 2's complement notation, and we want the computer system to perform this job, right? And then make sure that it does the job correctly. Okay, so now let's do this. So with the 2's complement notation of 4 bits, so what is the value of 4?
100. 100.
Okay, 0, 1, 0, 0, right? And the 2.
10.
Okay, so we can add these two, 0, 1, 1, 0. So the result is 0, 1, 1, 0. So because this most significant value is 0, so that's positive number. So for the positive number, that's basically means 6, right? So that's 4, that's 2. So the 4 plus 2 is 6. Okay. Now, what is the 2's complement representation of -3? Okay, so first we need to actually check the number 3. So that's 1, 1, right? Add 2, 0 for -3. Okay, now what's next step? Invert, right?
Add 1.
Add 1. That's 1101. So that's 1101. Okay. Now what about -2? -2. So first the absolute value, which is 2, and you got 1000, right? 0010. And invert it and +1. So it's 0, 1, 1, 1. So it's a 1, 1, 1, 0. So this is tooth complement, 2-tooth complement notation. Okay. Now when you add this is a 1, this is a 1, 0 plus 1, and this is 0, right? And then you carry 1 to the next position. So now you have a 1, 1, 1. So 1 plus 1, that's 0, 1. A 1, 0 plus 1, that's 1. And I carry next to the next position, that's 1. So it's 1, 1, 0, 0, 0. Okay. Now, this is a trick because you try to represent a number of tooth complement notation using 4 digitals. But when you add these two numbers,
is your mic turned off?
Okay, let me.
We can hear, Professor.
Can you hear me?
Yes.
Okay. Let me actually change.
It's my end. I'm sorry.
Okay, that's okay. Yeah, I just want to make sure my side is okay. So okay. So, but when you add these two number, you got 5 digitals. Okay. So that's a kind of problem, right? So let's see. So let me actually do this again. Okay. So let me actually erase that part. So make it clear. So this is actually the part we need to, spend more time on this. So now here's the operation we want to do ourselves. -3 plus -2, which is -5. And we want the computer to do it. So when the computer actually represent using the tooth complement for these two negative number, okay? So this is going to be -3 is 1101. -2 is 1110, right? Remember, we convert this into tooth complement. And then we perform the addition. So we're going to 1 plus 0, that's 1. 0 plus 1, that's 1. 1 plus 1, that's 0. And then you carry 1 to the next position. And then, so you have a 1 plus 1, this is 1, 0. And plus another 1, that's 1, 1. So you got a 1, 1. So you got a 1, 1, 0, 1, 1. Everybody got the question on this? I want to make sure everyone understands this addition over here. However, the result is 5 digitals. But we are actually working on the system, the tooth complement system, using 4 bits. So if the result come out with 5 bits, what we're going to do is, in the system going to get rid of this number, because only keep 4 digital, because that digital is actually out of this, out of this actually 4-bit range. That's important. If you actually add a tooth complement notation, when you add these two numbers, and if you actually you got the result, which is actually 5 digitals, then you're going to get rid of the most significant bit. Okay. Once you get rid of this bit, then you're going to keep that one as a tooth complement notation. Okay. Now that's the result. 1011 is the result. You get rid of this one here. Okay. Just keep that in mind. Now, what does that represent? 1011. What is the value, decimal value for 1011? Tell me.
7? No.
Okay. You must be careful in terms of.
7.
Okay.
8, 9, 10, 11.
Now, remember that's tooth complement representation. Tooth complement representation.
So 1 represents negative.
Yeah. So that means that's a negative number, right?
Yes.
Okay. So now if it's a negative number, when you convert it into a decimal, the first thing you need to do is invert, right?
Yes, 0, 1.
Okay. So now, what is this number? Oh, then plus 1, right?
We should add 1.
After inversion, after inverting the bit, add a 1. So that's 1, 0, 1, 0. And now what is this?
It's 5.
This is 5.
4 plus 1 is
5.
Okay.
It's 5. Since it's a negative, right? So that's
Negative 5.
it's negative 5. So that's actually the result. So when you actually, the computer system gonna perform this operation, add this number. You know, here, -3 is represented as 1101. -2 is added, is represented as 1110. When you add these two numbers, you got this 4-digit 1011 because the digital on the, on the leftmost one, the most significant digital is discarded because it's actually beyond these 4 bits because we only keep 4 bits. So that's the 5th bit. So, and then this bit's going to be represent the result, and that result represented by -5. So if we have 2 negative numbers add together, you got the -5, which is correct, right? Now, the next thing I want you to do is I want you to actually perform the tooth complement operation for these subtraction. So it's a 7 plus -3. So it's actually 7 minus 3. So this is subtraction. So in subtraction, when you do the decimal, we have to minus 2 numbers. The first one minus the second one. But if we use tooth complement, then we can, perform the addition as far as we represent both number in terms of tooth complement representation. So I want you to perform your own. I give you like 4 minutes to do that job. Okay. So first thing you need to do is write the 7 in terms of tooth complement notation, and write this -3 in terms of tooth complement notation, and add the tooth complement notation, get the result, and convert this result back to see whether this result matches the correct answer. You see the point here? Convert 7 into tooth complement representation. Convert -3 into tooth complement representation. Add these two tooth complement number and get the result, and convert this result back to see whether the result matches the correct answer. Okay, I gave you 5 minutes. So then we can actually, we will come back and discuss. Okay, so let me actually erase that one. Let me erase this one, erase this one to see how you're gonna perform. Okay, I'll be back in 4 minutes. I gave you 4 minutes to work on this. So